Good morning, everyone. Welcome to the EasyPower Tuesday Refresher webinar series. My name is Jim Chastain. I'm Applications Engineer here at EasyPower, and welcome you to the conference today. The presentation is specifically based on Introduction to Protective Device Coordination. Basically, it's not an in-depth treatise on the topic. What we want to do is focus on the use of EasyPower and the information that you can gain using EasyPower as you develop your system, which will allow you to do a better job of coordination and protecting the system. So again, we're going to be focusing on the properties of EasyPower in this respect, and how to use that information to set up relays and verify the performance, specifically for transformer protection and then coordination with other devices. We will not probably touch on the smart PDC. We'll save that for a later time. And I welcome questions at any time. So as you set up a transformer in EasyPower, one of the things that you'll notice that gets verified is that the standards that are used in the tool are based upon specific publications from the ANSI files, based upon whether it's a liquid-filled or a dry transformer. And these documents define specifically the properties and the terminology that's used in describing transformer damage. For instance, they talk about or define the thermal damage which will occur more likely based upon certain current and time limits, and then the area of the curve of the display, which we call the transformer Z curves, which potentially could result in mechanical damage. And then the guidelines that we're going to be talking about are based upon informed engineering judgment, not necessarily rules from any organization. And when you set up a transformer in EasyPower and then display the Z curve using the coordination module, which we call Power Protector, you get something that looks like this. And based upon those definition of terms, the thermal damage is this area of longer exposure to current at this level. We noticed the TCC curve has current on the horizontal axis and time on the vertical axis. And so if we plot a particular coordinate of time and current, the relationship to these curves gives us an idea of whether or not there's a potential for damage. Invariably, or most of the time, you'll see a two-curve plot. The dotted curve is 100% damage curve that you never want to exceed at any cost. The solid line is the single line 58% reduced curve for a single line to ground fault. And this is due to the fact that we're using a delta Y transformer, and a single line fault on the secondary side will be sensed differently than it would be on the primary side. So that's why, and this is only for a through fault and a single line to ground. The jog in the curve is meant to indicate the frequent fault versus 100% withstand. And again, in those standards that I referred to earlier, they define the frequent fault terminology, the size and transformers, and the number of faults that a transformer of that size can absorb. And so when at all possible, you want to avoid excursions into this area, but the curve tells us that the transformer would survive some limited number of faults that exceed this particular value, as long as it doesn't exceed the max value. The inrush current is this dot down here, and it's again a factor of a number of elements that are used in the definition of the transformer itself in EasyPower. And these can be adjusted based upon those parameters. But by all means, we don't want to have any protective device sensitive enough on the primary side to allow activation because of this particular inrush, which means we need to stay up and to the right with any protective device for this transformer on the primary side. Now, sometimes when you plot a curve, you'll only end up with what appears to be a single line, and this is because the two curves overlap each other, but it's the result of having a high resistance ground in the ground path of the Y side, or the secondary side of the transformer. So consequently, there's no concern about the single line to ground offset, and we would look at a specific current level that we would set a relay to trip at based upon, and this will be orders of magnitude different based upon having the resistance in series. So we'll get into more of that next session when we talk about ground coordination. Okay, so transformer protection basically is it's a widely known or accepted guidance that you really can't protect against an internal fault with anything that you sense a current on, and any through faults or any overcurrent relays are really detecting through faults. Now, the gold standard for transformer protection is really a differential relay, because it has the potential to be set on a more sensitive basis, comparing the incoming current into the transformer versus the outgoing current, and that difference will be the level that triggers the relay operation, and that can be resolved much more finely than the total overcurrent or even instantaneous overcurrent that we would sense through a CT. We'll talk about a little bit more of that at the tail end of this. What I'm going to focus on first are the through faults. The overcurrent relays basically serve as a backup to any type of transformer protection in the form of a differential relay. But EasyPower will simulate the relay breaker delay at the fault levels indicated. And just as a side note, because this comes up fairly frequently, internal fuse protection for transformers that a manufacturer may use doesn't really affect arc flash calculations. It's strictly installed to prevent a worst case mechanical failure or reduce the potential for fire damage. And so it really doesn't come into play when we're talking about system protection. Okay, routinely when we're talking about transformer protection with the relay, the recommendation is to use a very inverse curve geometry. And the National Electric Code recommends that the possibility of having protection as high as 6 times the full load current, if we fall into this particular plot or graph on comparing impedance and the voltage and whether or not it's supervised or unsupervised. So this gives us the range whether we're using a relay, a breaker, or a fuse. So these are basically the limits on protection above and beyond the rating for the transformer. So again, what I want to focus on first is how to use EasyPower to determine what these set points are. So first of all, we need to determine what the full load maximum current is under normal conditions. And in this case, we have a recommendation to set the primary pickup or protection at a range that's in between 10% and 40% greater than that full load current. And then make sure we're not violating the table. Now, in terms of a through fault, we want to make sure we don't exceed or we don't have the potential for exposing the transformer either to thermal damage, mechanical damage, and then we adjust the knee in the curve, that's the very inverse plot, so that it avoids that Z area in the damage curve. And then because EasyPower will tell us what the maximum fault current is for a downstream fault, we actually have the ability, and very frequently it's a desirable function, to set an instantaneous trip at some point that we know will not be exceeded by normal operations, and still would be much greater or much less, much better protection than the maximum fault current on a through fault. And so we're going to talk about, and at the same time, not violate the inrush plot on the curve. Okay, so just for calculating purposes manually, we're going to be using a transformer that's a step down from 115 kilovolts to 13.8 kilovolts, has an X over R rating of 8%. It's rated just under 30 mega VA. And by hand calculations, we see that the full load current on the primary side is going to be 150 amps. Now, the max fault current is something that we need to use EasyPower to determine. So let's jump into the tools and talk about this. So right now I'm going to talk about this transformer and really only this relay, which is going to be our overcurrent protection, and then ultimately the differential relay, which is going to be the gold standard, if you will. As I select the transformer and go into coordination, it's telling me that we have errors. It's because I don't have the relay set up. I don't want to really look at the errors right now. So let's just look at the transformer plot itself. And what we see, because this is a grounded transformer, a high resistance ground, we just have the one curve. And at the top, we see that the full load current for this transformer, if I line up my, I'm looking down here on the bottom indicator bar. If we align our cursor with that current, we see that it's 1282 amps. You might say, Jim, we just indicated that this was 150 amp full load current. Where is it? Well, what we're looking at is the plot on a 13.8K reference. So I'm going to change my plot area to 115K. And now I see when I align my cursor with the full load current, indeed I get the 150 amps. If you look down here on the indicator bar, my cursor on that full load current is 150 amps at 865 seconds. So that's the full load current. And so no matter what I do, that's the maximum current that the load should ever achieve. Now, at the same time, I want to calculate what the maximum fault current is. If I double click on the bus, on the main switchgear bus at the bottom, I see that the maximum fault on the secondary is 9,301 amps. The maximum current on the primary, and again, this is the worst case fault, so we have a half cycle, three-phase voltage fault on the secondary of the transformer. The maximum current that we will see on the primary is 1,116 amps. So this is a fault current that anything above that we know has got to be an internal fault. This is the maximum through fault that we'll see in the system. So this gives us the guidance now to set up our relay. All right, so we indicated that we have 150 amp full load current, and we've indicated or determined what the worst case fault current is. And that allows us to do the setup. We're going to set the trip settings for the primary tap to be 200 amps, which is roughly 30% above the full load current. We're going to use very inverse, and we're going to set an instantaneous current again, because we know what the maximum current, fault current, we'll see for a through fault. We'll set that at 25% above that 1100 amp range. So if we go back to EasyPower, let's see if we can't set this up. All right, so we're talking about the overcurrent relay R18. We want to set up the device function of 5051. We're going to set this for 200 amps, which should be times 5. And we're ready to set an instantaneous trip of 1400. So let's pretty close. Looks like it's going to be about 35. All right. So with that, now we have the relay set for protection of any current detected on the primary side of the transformer. Now, go to short circuit focus, look at the fault current. We can see the tripping. The branch fault current is 1116, which we saw, and we see where it's being cleared on the 5150 function at a little over half a second. Right? So I'm looking at, this is just my arc flash hazard report, which shows me the current on the secondary fault. Now I can look at the same thing if I come back to my coordination and I pick out the relay, the transformer, and plot them. So we can see with this, we've got fairly decent protection. We're clear of the inrush. We've got an instantaneous trip that we know will never be achieved with a normal through fault. And we're off. Actually, we may want to set the curve up a little bit. So there's two things going on here. The R18 set point, this is the instantaneous set point. No, this is the pickup set point that we set for 200 amps. If we left click and drag, we'll change that. We could change that to see how it's going to vary in the performance. Let's leave it set at 200. And then if we wanted to adjust the time dial on the curve, we would be able to do the adjustment here to match up with any other devices we're trying to coordinate with. Okay, so that's a good start. We'll leave it there for now. I wanted to spend some time talking about the differential relay. So I'm going to close this plot, not save it for now. Now the differential relay is again determined by the difference between the current flowing into these CTs compared to the current flowing out through these CTs. And so that's something we can't simulate, that difference, because it can be set at a very small differential to be able to trip the relay. So what we're looking at is a manufacturer's data sheet for differential relays, because it's determined by that zone of protection, which is dictated by the placement of the CTs. And a result of having that very fast response, we are basically counting on the manufacturer's data sheet to tell us what the response time is for this relay if these CTs trigger that relay to trip. And so if we look in the manufacturer's data sheet, we see roughly for the amount of current that we're talking about, just under 2000 amps, the differential time is going to be just under 50 milliseconds. The response time in milliseconds, and then the multiples of the pickup and operating current. And this is based upon the user's manual for this particular relay. So again, the response time is a fixed recommendation from the manufacturer. If we go back to EasyPower setup, this is not something we can invoke in the relay itself. So what we've defined is we've set up this particular relay manufacturer's graphic. Let's go back to database setup. When we set up this relay, we've only indicated the manufacturer, the type, and then the label that we want to put on the one line. We haven't done anything else with the settings. And I'm going to go back to the response time now needs to be reflected in the properties of the downstream bus that we're protecting. And so when we go to the arc flash hazard tab, currently it's set up, and we saw when we faulted that bus, we saw the TCC times as reflected in that overcurrent relay. But now we also want to include the possibility of incorporating user-defined times. So we're going to use both user-defined and TCC. And now if we end up tripping on the differential relay, I think it's an 87. And we know from the manufacturer's data sheet, response time is 50 milliseconds. So now when we get a fault on that bus, it should reflect both the defined time and the TCC plot. So now when we go back to short circuit focus, I'm going to double click on this bus, look at our range for arc flash, and sure enough, if that relay, the overcurrent relay trips, the response time is a little over 1 second. If the differential relay is the responding device, the response time will be 50 milliseconds. Now again, we need to include, if we have a delay because of breaker opening time, we need to include that in that response time that we're entering it. But the point is that the tool will give us both of these properties based upon the way we've set up and defined the one line. Okay, so what we've done in this session, we've defined overcurrent protection through an overcurrent relay, and EasyPower is using the response time and the opening time of the breaker that it's triggering. And we've defined a response time for a differential relay as a fixed time, and it's up to us, frankly, to set up the relay differential trigger point to enforce that particular response time. Okay, I think that covers what I was wanting to touch on. Let me see if we got any questions I can deal with. Yep, we can provide slides, no problem. It'll be about a week before we get this posted. We do have regional training. We're going to be setting up actually live regional training probably starting in the fourth quarter. Meanwhile, we have online regional training every quarter, and we're doing arc flash workshops every month. So thank you for attending. By all means, if you've got more questions or more details that we can help support, contact tech support at easypower.com. Thank you for attending.